this hour, we'll just go quickly through the main properties of them, the main equations, so that we are sure that there are no gaps, because in the remaining weeks of the course we will use the transistor quite a lot. Now, this is not a cross section, but a view sketch of P-substrate technology, in which we have an NMOS and a PMOS transistors. So the NMOS transistors, they're directly implemented in the P-substrate. And here what we have is the P-tap. This is the bulk connection of the transistor, how the connection through which we bias, put the potential of the substrate. And you see that it needs to be always the lowest potential in our solution, so that this parasitic capacitance, this parasitic diode that we have here between the drain or the source area, which is N plus area, and the P substrate is reverse bias. So this parasitic diode should be always reverse biased and not turned on. Otherwise, there will be big currents and will melt our device. So this is the bulk connection, and we have here an area for the drain and an area for the source, which are N plus sockets. So these are areas which are doped with donor atoms inside the P-type substrate. This is the length of the transistor, and this is the width of the transistor. So this eventually will become an NMOS transistor, because we will create an N channel. We can also implement P MOSFETs. For this, we will have a local well here, N well, and then this will act as a local substrate for this transistor only. And then we'll have to bias it. So in this case, it's an N-tap, so an area with the N plus doping, so that we have a good contact, and we'll bias it to the highest possible potential. Because here the diode, the parasitic diode, N plus diode, is in the other direction. The areas for the source and the areas for the drain are P wells inside the N well. And this eventually is also here the local substrate, or the well, is N, and when the transistor operates and the interface below the oxide is inverted, we'll have a P channel, and has the name P channel transistor. So this is the NMOS transistor, and this is the PMOS transistor. And we have basically three main modes of operation of these devices. Here, for completeness, I listed 4. We can either have them in saturation or in the triode region, whereas the saturation is that the current through the structure only weakly depends on the voltage, drain source voltage. This is the saturation. And then in the triode region, the current depends on the drain source voltage in the triode region. You know this. And then for this saturation triode region, we also distinguish 2 main regions depending on the channel. So either in subthreshold or above threshold. And this is given, of course, by the gate source voltage. Either gate source voltage is below the threshold or the above the threshold. If the gate source is very much below the threshold, there is no channel, so there is no current. It's not listed here. But if it is the gate source voltage is close to the threshold voltage, then we are in a subthreshold region, and the current is exponentially depends on the gate source voltage. So the current from 0 starts exponentially increasing with respect to the gate source voltage. And then if you are in a subthreshold region, in triode region, which is a mode of operation which is almost not used, so I listed here for completeness, but then the current dependency is exponentially dependent on both gate source and drain source voltage. Then if you are above threshold voltage, or the mode of operation in normal electronics, in most of the cases, gate source voltage above the threshold voltage, then there is in saturation region, there is a square dependence of the current on the gate source voltage, and in triode region, there is a linear dependence of the current on the gate source voltage and square dependence on the drain source voltage. So now, let's start with all terminals of the device connected to ground and an NMOS transistor. Any analysis that we'll do for the NMOS transistor is easily transformed for the case of PMOS transistor by applying the principle of duality. The principle of duality is that you substitute your exchange for PMOS transistors all P regions to N regions, and you invert all the voltages. And then also electrons you substitute with holes, etc., etc. And then anything that is set for the NMOS transistor mostly applies for the PMOS transistor. So as a basis for our discussions, we will use NMOS transistor. For NMOS transistor, we start with a P substrate, and then we'll start connecting all terminals to ground. So you have this situation. So there will be no channel here, and there is no current that can flow from the drain to the source. Here, these parasitic diodes, PN diodes, they're in thermal equilibrium, of course, so also no current, and that there is a certain depletion region in the interface, NP interface. And this region, of course, extends mainly in the P substrate, because usually the P substrate is weakly doped, and the contacts for the source and the drains are in areas with heavily doped N+ materials. So it's a one-side junction. All right, now step 2, we apply some voltage at the gate, and we apply some small voltage in the drain. So the voltage that is applied on the gate is more than 0, it's a positive voltage, but it's still less than the threshold voltage. So what will happen is that we will create a vertical electric field in this direction from the gate to the substrate. Keep in mind that the substrate is biased to 0. Now, this electric field will exercise force on the mobile carriers in the P substrate, which are holes. So the holes will feel the force of the applied field, and they'll move away from the interface of the oxide. So we chase away the holes. Now the holes will leave behind the negatively charged ions of the acceptor atoms. And then depletion region is created here under the gate, in which we have as charge only the negative ions, which are immobile. So we don't have any mobile carriers, because the mobile carriers, the holes, are chased away from the interface. However, there is still no channel. Keep in mind, there are no carriers, so no electrons can go from the source and arrive at the drain. And still we say, generally, the structure does not conduct current from the source to the drain. So let's see if I forget something. Yeah, leads to an electric, holes escape, a depletion region is created. Yeah, something interesting here, the buck through this connection cannot set any more directly the potential under the gate. Because here, now if you look at this potential here under the gate, it is between two capacitors in this picture. It is between two capacitors. One is the C oxide, so the gate, how it controls the interface, and it is through the depletion capacitance. So this depletion area creates a depletion capacitor, is controlled through the bulk. So the bulk cannot set here 0 potential. So this potential actually increases. Now, if the gate voltage reaches this level, which is the threshold voltage characterized in the technology, then we start collecting actually, so electrons from the source area can now come here. So we invert the interface in the substrate. It used to be P type, so with majority holes. We chased away the holes through positive voltage at the gate, and now the voltage is so much positive at the interface here, semiconductor oxide, that we start collecting electrons from the source. And channel is created. And when we have electrons which pile up here in the interface, they will eventually extend all the way to the drain, and they'll create an area which behaves like an N-type semiconductor. We inverted the channel. There is inversion of the interface below the oxide. So let me see. Weak inversion begins when the electron and the hole's densities are about equal. At threshold voltage, the electron density at the interface is greater than the hole density. When the density of electrons is greater than the hole, we're getting into the strong inversion. And for voltages, gate voltages higher than the threshold, leads to the formation of a conducting channel between drain and source. And now, if we apply certain voltage at the drain, it will create a drift force along the channel. So electrons, if there is a channel, electrons from the source can reach the gate, can reach the drain, which is equivalent to saying that there is a current flowing from the drain to the source, and the device conducts. Here is, in this cross section, is the channel illustrated. So these are the electrons. Below them there is still depletion region, and this is now the P substrate. And then through this channel, which behaves like an N-type semiconductor, provided that we apply some drain voltage, there will be a horizontal electric field which will exercise drift force on the carrier's electrons in this case, and then electrons from the source can propagate to the drain. Equivalently said, there will be current flowing from the drain to the source. The channel is inverted from holes to electrons as main carriers and thin layer under the gate. Yeah, one very important thing, and this is you have to now just memorize it for all your life. See the bulk. Bulk is always the lowest possible potential in our circuit, and this is because we want these parasitic diodes to be reverse connected. So we don't want any currents flowing through these areas into the substrate. And this is achieved if the bulk is at the lowest possible potential here. Right. Now, the modes of operation, just briefly, most transistor modes of operation, we distinguished with respect to the gate voltage several modes. So we have the subthreshold mode of operation. If the gate is lower than the threshold voltage, transistor can be in cutoff region, or if it approaches the threshold voltage but does not exceed it, we are in a weak inversion mode of operation. So there are some electron carriers, so there is some small current that is being conducted. It's a valid mode of operation. There are circuits designed in this mode of operation. We'll discuss this. Then saturation and triode region, usually we discuss this in the context of strong inversion. Strong inversion when there is a channel. Theoretically said, strong saturation and triode also applies to subthreshold region, but only saturation region. Saturation mode of operation in subthreshold region is something useful. So this is why we separate. When we say saturation and triode, from now on we will understand only strong inversion. And when we say weak inversion, we will understand subthreshold saturation. Now, we will consider now the large signal model, how we can model the behavior of the MOSFET. And what I recommend always to students is memorize the equation of the current in triode region. And this is the equation of the current in triode region. Why it's very important? Because in most of the design cases, you consider either cutoff, no current, or triode region, which is this equation, and saturation region. And saturation region, the equation of the current in saturation region can be very easily derived from the equation of the triode region. So if you memorize this equation, you actually know the equation for the current in saturation region. Now, the complexity in integrated circuits is very high. So this equation will be very inaccurate equation if you see the behavior in integrated circuits. in the actual transistors, we will use much more complex models that will take many effects into account, and the amount of details that will be captured by our models is unperceivable for us. It will be too difficult for our brains, and also will be very accurate, but we will lose our intuition of what's going on. So for accurate results, we will always use simulation tools. We will always use cadence. However, we are the engineers who take the decisions about the architectures, about the design of the circuits, and what we have to do, how we have to optimize our circuits, and what we have to put in our simulators so that we get the accurate results. And for this, we need to have intuition. And to build this intuition, then design on paper, on scratch paper, is very important. And for this, we'll need these equations, and we'll know, and we have to capture the main trends. If you increase the drain source voltage, what will happen? If you increase the gate source voltage, what will happen? If you increase or decrease the size of the transistor, what will happen? So what we have in this equation, the triode region of, it gives the dependence of the drain current with respect to the input of the transistor, which is the gate source voltage, and the output voltage, the drain source voltage. So gate source voltage and drain source voltage. And then we have the dimensions of the transistor, W over L, and some technology constants, the mobility of the carriers at the C oxide. So this is usually given. This is a design parameter, and these are also design parameters. So this gives a basic intuitive equation, assists our understanding, and for exact prediction we'll use cut. The mobility, of course, here for electrons, NMOS transistor is mu-n, and for MP is, for the PMOS, is the mobility of the holes. And here is again a point that you can memorize directly. You know from semiconductor physics and materials that the mobility of electrons is about 2-3 times higher than mobility of holes, which means basically that for the same dimensions transistors and for the same biasing conditions, the NMOS transistors will generate more current, about 2-3 times more current than the PMOS transistors. So if you want to equate the currents, this will mean that the lower mobility of the holes will have to be compensated with a larger W and L of the transistors, which means for IC designers that if you design with PMOS transistors, you have to design with bigger transistors. And designing with bigger transistors means that you have more parasitic capacitances and hence slower circuits. So often in jargon among engineers, we say PMOS transistors are slower. They're not fundamentally slower because the holes are, the mobility of the holes are slower, but the mobility is slower of the holes, but they're slower because they have more parasitic capacitance, and more parasitic capacitance means that the time constants are longer, and this means that to charge and discharge the nodes around the PMOS transistors usually takes a little bit of more time than NMOS transistors. So C oxide is the capacitance of the oxide, and there are 3 main regions of operations. And in this course, I consider the overdrive voltage, gate source minus threshold voltage, as V on. And this indicates me how much the transistor is turned on. This is the overdrive voltage, what we discussed in electronic circuits. And this is the difference between the gate source voltage and the threshold voltage. So now simply we can say if the overdrive voltage or the V on is less than 0, then we are in subthreshold region. If V on is positive, larger than 0, but still lower than the drain source voltage, then we are in saturation region. And if V on is larger than both 0 and drain source voltage, we're in the triode region. And then in the current drain source voltage characteristic, or the output characteristic of the device, if we plot this equation, it will look like this here. And then when drain source voltage, this drain source voltage becomes equal to the on voltage, then we enter, we change from this region of operation, triode region, into saturation region. And in saturation region, we lose this dependence, and then the current saturates. And this has to do, of course, you know, from semiconductor physics and materials, with the pinch off of the channel. We will have a chance to rediscuss this again in the following slides. So let's start with subthreshold region and the cutoff region. If the gate source voltage is lower than the threshold, simplistically you can say the MOSFET transistor is off, or the drain source voltage is 0. Realistically, the channel inversion begins as the gate source voltage approaches the threshold voltage, and some electrons from the source region can jump into the forming channel and can conduct current and can reach the drain. The most important thing, we discussed and analyzed this in semiconductor physics and materials course. The most important thing that you should memorize now is that dependence of the drain source current with the input parameter of the transistor, which is the gate voltage, gate source, this dependence is exponential dependence. So if we increase a little bit the gate source voltage, the current will jump exponentially. And there is this factor n here, the exponential characteristic, which is given by the ratio between the depletion capacitance and the C oxide capacitance. Keep in mind what we said for the channel, for the interface, on the interface between the oxide and the semiconductor. From the top side, we have the C oxide capacitor, and then the gate voltage controls the potential in the interface. And from the bottom side, we have the depletion capacitance, and the bulk contact controls this potential. So the potential is somewhere in between. And this factor, so basically the ratio between the drain and the oxide capacitance, forms this factor here, n, which in most cases common value is 1.5 volts. And again, what you need is only intuition. You don't need an accurate result, because the accurate result you'll get from the simulation tool. So if V on voltage is much smaller than 0, you're in cutoff region. You can say that here this voltage is so small that this exponential characteristic is negligible. But you will still have current. And this will be the reverse current from the parasitic bulk drain and bulk source diodes. So they are in reverse bias, these parasitic diodes, but there is still some small current conduction. In modern IC technology, when the transistors are very small, you know that we have to also scale down the thickness of the oxide. So we discussed this, that in modern technologies, so you have the gate, so this is the gate, you have here an oxide, and you have here the P substrate. This is the gate. If this thickness becomes very small, then what you also have, is not captured in the slides unfortunately, is that some charges here, some charges, some electrons, or can tunnel into the substrate, and this is a tunneling effect, which we discussed in semiconductor physics and materials. But particularly for larger sizes transistors, this current can become significant leakage current, and this will be, it's not captured here, but it will be current from the gate to the bulk, a leakage current, and this is a concern for modern technologies, particularly large digital circuits, and as the transistors become many in numbers, and then statistically this small current that tunnels from the gate to the substrate piles up, and can become significant leakage current. This effect, by the way, is modeled in the dummy 45 technology that we will use for our part B, for our practical assignments. So you can observe it. All right, now let's increase the gate source voltage, and then we start approaching the threshold voltage. V only still negative, but we are in a weak inversion, so the channel begins to form, and then we have the exponential characteristic between the drain current and the input voltage, the gate source voltage. These are the equations for semiconductor physics and materials. The most important thing that you have to remember about this mode of operation is the efficiency to generate GM. So the GM is, you know, the small signal parameter, which is the gain of the transistor. So for smooth variation in the gate voltage, what will be the variation of the current? And we model this with GM. This is the gain of the transistor. This is how we make gain with a MOSFET. And to make a gain, we have to invest current. And we invest this current, biasing current. This means investing in power consumption. So to realize a gain in a transistor, we have to pay with power consumption. Higher power consumption means higher gain that we have, GM. In weak inversions of threshold mode of operation, because of this exponential characteristic, if we take the derivative of the drain current with respect to the gate source voltage in order to get the GM, this strong characteristic will give us exponential characteristic for the GM of this type, if we substitute here. So what we have is here the biasing current, the drain. This 2/3 comes from the fitting coefficient B or N in the previous slide. And we have here KQ over E. And now you can calculate this for temperature 300 kelvins, room temperature, and you get a constant actually. If you divide now this to the biasing current to get what is the efficiency of creating transconductance gain, and you get a number of 26. So something, yeah, here is calculated. And this is the highest possible efficiency that you have in the operation of the MOS device. So this means that it's small gain, it's small GM, yes, but also it's small investment of current. The biasing current is still very low. So the efficiency of investing, so what you get, and this is gain, and what you pay, and this is the biasing current, this efficiency is the highest possible. And this is why in ultra low power electronics, for very power efficient designs, this mode of operation of the transistor is used, because the transconductance gain efficiency is the highest. Yeah, here is calculated, and then for room temperature, you can calculate the gain efficiency to be 26 of 1 divided by volt. However, because of that the threshold voltage here, or V1, is in the exponent function, this means that any mismatch of the threshold voltage will give rise to a very large mismatch in the drain current. This means that, yes, in this mode of operation, we will we can design very power efficient circuits, but the mismatch that we have to tackle, we have to solve is also is largest. Also the temperature dependence of this mode of operation is very high, because you see that the temperature is also in the exponential function. Actually, everything that is in the exponential function makes the current very sensitive. So these are the challenges and the problems that we have to solve for power efficient electronics. In addition, this mode of operation also concerns low speed circuits. And this is because the current, the biasing current, and the currents in general in this mode of operation are very small. And then relatively, the parasitic capacitances will be large. So we'll have to charge and discharge some normal parasitic capacitances with extremely small currents, and this will require time. And hence, the electronics that we can build in this mode of operation is usually low-speed electronics. So this is for lower frequencies. Now let's go to above threshold. So gate source voltage is above the threshold voltage, or and the V on is larger than the drain source voltage, and then we are in the triode mode of operation. And V on is, of course, the overdrive voltage, gate source minus the threshold voltage. So basically, what I'm saying here is that the gate source voltage is above threshold voltage, and the drain source voltage is small. Let's see how it works with drawing. Let's see. So I have now a gate here. This is the oxide. And plus is the source. And plus is the drain here. Now, gate source voltage is above threshold voltage. And now, the drain source voltage, so from here to here, is low. Yeah, so it's here low. This allows me to have the channel. So this makes sure that I invert the interface. So I have electrons here. So I have a channel between source and the drain, and I can conduct current. Current can flow. And because the voltage, the drain at the drain side is low, so this is for example ground, and this is a low voltage, I can assume that this voltage here is approximately as this voltage here. So say that these potentials are approximately equal because the drain source voltage is small. If this potential is approximately equal, then the density of electrons in the channel, the density of electrons will be almost the same. So this means that I can consider this channel as a resistor with certain conductivity, certain resistance. And the transistor will conduct current like a resistor. So if I increase this drain source voltage, the current will be increased. So in this mode of operation, you can just say that the MOS transistor behaves like a resistor, and this is valid only if the drain source voltage is small. Then you can just write the equation. This is the current in triode region, the complete current. And then you see if drain source voltage is small, this becomes negligible. Yeah, and then you can define this as G, conductance, and then G is 1 over R ohm. Then you can define the ohm resistance. This will be the resistance of this channel, and then the resistance, you can express it from here to be equal to this. And of course, if you increase the size of the transistor, you know, it's like putting resistances in parallel. So the resistance, the total resistance will drop. If you increase the L, the total resistance will increase. All right. Now, what will happen if I increase drain source voltage? Now, so this analysis is the so-called mode of operation for linear ohmic mode, in which the transistor in triode region behaves like a resistor. If I increase a little bit the drain source voltage, but I'm still in the triode region, so this assumption still holds. V on is larger than the drain source voltage. But now I must take into account this quadratic term here, this quadratic term. Yeah, so I have to take into account. Then I'll see this curvature of the characteristic. So it's no longer here linear like in this region, but now it has curvature. So the current, by increasing the drain source voltage, the rate of increase of current decreases. And why is that? This is because of this this term. And the reason for this, we discussed this in semiconductor physics and materials, is that when I increase now this voltage here, so now drain source voltage increases. This is ground, so this potential increases. Now, this voltage, which is here gate drain, if this potential increases, this gate drain voltage actually decreases. And at certain moment, and this voltage here determines what will be the density of charges in the channel. Yeah? So I'm still in triode region. This voltage is here, gate drain voltage is still larger than the threshold voltage, but it's not that much larger. Here in the gate source voltage, it's very much larger, so I have a lot of electrons, because here with this large voltage, I can invert the channel very well, and the density of electrons here is high. But now, as I move towards the drain, if I look at the potential here in this interface, I start from zero potential and I move to a voltage which is high, the drain voltage. So if this potential increases, this means that the gate voltage and this point X along this channel decreases. And if this voltage here, potential difference decreases, this means that the density of charges that I have in the channel decrease. So if I put, for example, density of charges like this, here I'll have small density of charge, and here I have a large density of charge. What does it mean, density of charges? I'll have basically less carriers. And if I have less carriers, this means that for the same, this means that the conductivity decreases, or the resistivity of the channel increases, which means that here, for example, I have you know, low resistivity, small resistor, and here in this part of the channel I have bigger resistivity. And this is why the current here saturates, and this gives the more I increase the drain source voltage, the less charges, density of charges I'll have in this point. So the resistivity of the whole channel from here to here, in total, the resistivity will increase. Its conductivity will drop down, and the current will start saturating until I reach this point, this magical point, which is the border between the triode region and the saturation. So now we are in saturation region. I exceed here, I further increase the drain source voltage, and now V on becomes less than the drain source voltage. So in this specific region, what will happen is that exactly at the point when V on is equal to drain source voltage, this is equivalently to saying that the gate drain voltage becomes equal to the threshold voltage. So when this happens, this means that here the channel is exactly inverted. So if I increase further beyond this point, this voltage between gate and drain will be less than the threshold voltage, which means that I cannot maintain the channel in the vicinity here of the drain. Of course, I will not drop down with the equation, so I will not follow this, because I cannot create charge densities which are negative. This is physically, the charge density just are zero. So I saturated zero. So then this means that the channel resistivity or conductivity of the channel will saturate to a certain value. Say this is the channel, and now this is my structure, and now here my drain source voltage is, so this is V drain, and this is V source here. This is the gate here. Now this is higher. So if I look at what's going on in the channel, and I look at the potential from this point, which is ground in the source, and to this point, which is drain source voltage, a higher voltage, in the channel I'll have gradient from zero to the drain source voltage. At certain point, this voltage will be between gate and this point will be exactly threshold voltage. Yeah. here I'll be much higher than the threshold voltage, and here I'll be less than the threshold voltage. So at this point, I'll have no channel. It will be depletion region. And here the most favorite question that I have from students: how then, if I have depletion region, the current can flow? And it can flow because here I have drift up to this point. So an electron starts from here and enters here, and it's accelerated by this electric field, the drain source electric field. Yeah. And at certain point, so this drain source electric field actually drifts, pulls the electron, and at certain point, it will get this electron will get out from the channel and will be in the depletion region. And in this depletion region, it will just accelerate very fast to the drain and to arrive the drain. So in depletion, it is depletion region if you look it from the vertical electric field. There are no carriers. But if you look it from the point of view of the horizontal electric field, there will be transient carriers, and these transient carriers will be the carriers of electrons which are injected outside the electrons, so they are accelerated and get outside the channel. They're in the depletion region, and they're pulled by the strong attraction force in the drain, the positive voltage here at the drain. So the difference of the behavior of electron within the channel and outside the channel is that here all the electrons are contained within the channel, because the major electric field that is dominant is the vertical electric field from the gate to the bulk. So this electric field, this holds the electrons together. At this point, this electric field, the horizontal electric field, drain source electric field, becomes dominant and puts in an uncontrolled manner the electrons into the drain. And then the current is determined by the conductivity of the channel from this point to this point. This will determine what is, the current, the moving actually of electrons within the channel. And here they are injected, and in uncontrolled manner they arrive at the drain. So because the channel pinches off, we cannot maintain the channel here. Its resistivity or conductivity also pinches off, and it does not depend very much on further on the drain source voltage. There is the channel length modulation. I know that you know this, and we'll discuss this as a second order effect. But as a first order effect, what we say is that at certain voltage, drain source voltage saturation equal to V on, this voltage, this equation is transformed into this equation. If you substitute this drain source voltage with V on, you'll get this equation. And you see that the current lost is dependence on the drain source voltage, and the current remains here. And it is determined by the conductivity of the channel. Now, of course, you have channel length modulation because the channel became a little bit shorter. You see that the channel became shorter. So this means that its conductivity effectively increased. And we can model this with the channel length modulation effect by applying a term here of certain dependence, coefficient dependence on the drain source voltage. And then the characteristic will be of the current will not be flat here, but it will increase like this. With increase of the drain source voltage, we will still have certain increase of the current. And this gives rise to the output definition of the output resistance of the transistor. And this is how it looks with the transistor cross-section with the pinch off of the channel. So I'm just recapping here the things that we had 1 month ago in semiconductor physics and materials. Because the channel became a little bit shorter, this means that its conductivity increases a little bit. And if you model the reduction of the channel by delta L, you can then derive this linear dependence and simplify to linear dependence drain source voltage in this lambda. Usually, we'll work then with this equation, where the lambda is the channel length modulation effect. So the characteristic without channel length modulation, with channel length modulation. So then I'll stop here for now. In the next session, we'll continue with the small signal parameters.